Welcome to lesson 13 of electricity, and we're on to electromagnetism. So the first thing we're going to look at is the effect on a magnetic field on a current carrying wire or on a charge. So we're going to look first of all at a current carrying wire and a magnetic field. So let's take this scenario. We have a north pole here and a south pole here. We know that for magnets, magnetic field lines go from the north to the south pole. So we have magnetic field lines here. We'll always use red for magnetic field lines at the moment, okay? And we're putting in a current carrying wire down here, right? Like that. Now that current carrying wire will experience a force in the magnetic field, okay? Because if you remember that a current carrying wire itself has a magnetic field, okay? So over here, if we draw this, okay, a magnetic field, there's a magnetic field around the current carrying wire, okay? The direction of the magnetic field, remember, the right hand grip rule, okay? So if I get a biro, if I hold, or a pencil, I hold it like that, and I have the thumb in the direction of the current, so I take the pencil to be the current carrying conductor. If the thumb is in that direction, the magnetic field is in the direction of the fingers as they wrap around the wire. So that's the right hand grip rule. But what's important here is that we have a current carrying wire inside in a magnetic field. If a current carrying wire is inside in a magnetic field, there will be another current carrying wire has its own magnetic field. It's inside another magnetic field. Where magnetic fields interact, there will be a force. Okay, so experimentally then, it was checked to see what did this force depend on, and it was found that it depended on the strength of the magnetic field. You know, that's magnetic field strength, the current flowing through the wire, and the length of the wire. They were the three factors, and in fact the formula is very straightforward. If the magnetic field, if the current carrying wire is perpendicular to the field, it simplifies down to F is equal to BIL, and that's the formula we need to know. F is equal to BIL, and that's it, okay? Now, that's the size of the magnetic field, or sorry, the size of the force in the current carrying wire. We also have to know the direction. For the direction, we have a nice method of remembering it. Okay, so for the direction of the field lines in a magnetic field on a current carrying wire, we have the right hand grip rule. For the direction of the force, we have a left hand rule, and it's Fleming's left hand rule. I remember it's like this, okay? So all three fingers are perpendicular, okay? The thumb is the thrust of the force, okay? So think of somebody plucking out your eyes with their thumb, okay? So, or using a thumb tack, you apply your force with the thumb tack. So that's your force. The forefinger, okay, the pointing finger is the force, okay, or sorry, is the field, my mistake, the field, the forefinger is the field, and the center finger is the current. The center finger is the current, okay? So the thumb is the thrust, be careful with the forefinger, it's the field, okay? The field, F for forefinger, F for field, and the center finger is the current, okay? And that's your setup, okay? Simple as that. So let's take a scenario where, as we have here, okay, the magnetic field is going from left to right, and the current is going down. So the field going this way, current is going down, and if we look at it, the force is coming towards you. So that wire is going to come out there and hit you. Okay, so that's how it operates. So make sure you can twist your way around that. There's a nice video clip in a minute to kind of reinforce that. Okay, so current carrying wire and a magnetic field experiences a force. That's number one. Okay, the force it experiences, okay, the magnitude of the force, F is equal to BIL. The direction of force, Fleming's left hand rule. Okay, why does it experience a force? Because the current carrying wire has its own magnetic field. The north-south poles are producing a magnetic field. If you have two magnetic fields interacting, as we'll see later, there will be a force. Okay, there will be a force, simple as that. Okay, so that's that. Now, the other thing we need to know here then is we need to derive one derivation, and the derivation is for the force on a charged particle inside the field rather than a current carrying wire. So, and to derive this, we start with F is equal to BIL, which was the experimental result. Okay, so let's have a look. at how we do it. Okay, so F is equal to B. Now, this is a kind of a pared down version, but what we're doing here will get you full marks, so we'll stick with the pared down version. We'll become a little bit rootless at this stage. Okay, so we have F is equal to BIL. Okay, we start with that. Now we want to end up with the force on a charged particle, which is F is equal to BQV. Okay, so Q is the charge on the particle, possibly an electron. V is its velocity. Okay, so we're going from here to here. So it's pretty clear we need to get rid of I and we need to get rid of L. Okay, so we have to get rid of I. Remember, we have our simple formula for current from previously, charge over time. Remember, current is the flow of charge and current is the charge flowing per second. Remember that formula, a little bit strange, it's not in the tables, okay, but it's very important. So I is equal to Q over T. And to get rid of L, we use our favourite formula, okay, our formula for speed. Okay, our formula for speed. So speed is distance over time. We use this time and time again, and then once again, not in the tables. Okay, so we just need to be aware of that. So these are the two we'll use. So let's have a look. Now, okay, here for Q, right, we're going to say that, okay, no, we'll just leave it as it is for the time being. So F is equal to BIL. So instead of I, we're going to put in Q over T. Okay, and instead of L, we're going to rearrange this. So L is V times T. We're going to put in V times T. Okay, we can see then we can cancel the T's and we're left with F is equal to B QV. Now, we then have to indicate, and we could have done it earlier, that Q is equal to N times small q. So if you have a charge Q, it's N times the charge of the individual particles that are causing the overall charge, large Q. So in other words here, so if the charge was 46 and each individual particle had a charge of 2, N would be 23. Okay, so instead of Q, we can put in NQ. So we get F is equal to B NQV. We can do that earlier also. Okay, and then for N equal to 1, okay, so if we're talking about one charged particle, that becomes F is equal to BQV, which is what we were looking for. Okay, that's it. That's how you derive that one. Okay, so that's the beginning. Okay, that's this one sorted. Have a look at the video clips, which will reinforce what we've just done. Okay.